Hello and welcome to the Big Bang, the Milky Way, and more, and NASA Explorer School chat. Today with Dr. John Mather. My name is Erin McKinley, talking to you live from Goddard Space Flight Center in Maryland. I'd like to welcome everyone joining us today, including on the webcast, as well as in our in-studio guests. If you happen to be in the NASA Explorer School virtual classroom and you are waiting to get into the chat room, go ahead and refresh your browser window and go ahead and log into that chat window. Today we have a very special program for you today. We are going to be joined by Dr. John Mather. Thank you for joining us today.
Thank you. Thanks for inviting me.
Thank you very much. You are a Nobel Prize winner for your studies with the Cosmic Background Explorer. Dr. Mather, could you just tell us a little bit about yourself?
Yes, sure. Well, I guess now I'm called the Senior Project Scientist for the James Webb Space Telescope, which is a new one. We're planning to replace the Hubble Space Telescope with it, or make a successor for the Hubble with it. To step back a few minutes in time, though, when I was growing up, grew up in the rural New Jersey and grew up on a farm, but it was a research farm, and so there were science labs nearby. So I got the idea that science was going to be really cool, and astronomy was getting to be exciting. So then I went to college and graduate school, and I thought I'm going to be a physicist. Finally, I found out about this cosmic microwave background radiation that we could measure that's left over from the Big Bang. So I found out about this while I was partway through graduate school and tried to do a measurement of it. So then that failed, but I went to NASA in New York City, and then I came here in Washington, D.C. area and in Greenbelt, Maryland, to work at Goddard Space Flight Center to work on the Cosmic Background Explorer satellite, which was going to go measure the Big Bang radiation. So how's that for an introduction?
That is fabulous. Thank you so much. And we have had many high school students send in questions for you today. Are you ready for these questions?
Yes, I'm ready for questions.
Fantastic. The first question we're going to go out to is from Blake in North Carolina. Let's take a look.
Hi, my name is Blake and I'm a sophomore earth science student at Scotland Early College High School. I would like an astrophysicist's explanation on how the moons in our solar system came to be.
So the question is, how did the moons in our solar system come to be?
Excellent question.
And it's really, actually, we're not 100% sure, because we don't know how anything really happened. We weren't there. Our atoms were there. Our atoms were part of the original solar nebula. So the idea is that the sun formed from a cloud of gas, and the gas had dust grains in it that were left over from previous generations of stars that had enriched the gas with heavier chemical elements. So the sun is forming down in the middle of this cloud, and everything's orbiting around this proto-sun. Gradually, the dust grains start to stick to each other, just like the dust bunnies grow under your bed at night. They only do it at night, right?
That's right.
So the dust grains will stick together, and eventually enough of them stick together to form large objects. And when they get to be like snowballs, and then they get to be bigger and bigger snowballs, and finally they start to get to where if one hits another one, it's a big deal. And so you can have a big crash of some sort. So it's the idea is solid material starts to stick to other solid material and gradually build up into bigger blobs. Eventually, the solid material can get heavy enough to have gravitational forces that can pull the gaseous material in and make bigger planets, even like the Jupiter, that has a lot of hydrogen and helium with it. So the moons are probably a lot of them either left over from the original formation of the solar system, or they've been reprocessed by colliding with each other. Sometimes we imagine some of them were formed like the planets were formed going around the central object. So you know Jupiter has 4 wonderful large moons, and they were probably formed already in place orbiting around Jupiter. Others, like our Earth's moon, are probably the result of collision between a very large object like the size of Mars and the Earth when it was much younger. And that maybe happened when the solar system was maybe 50 or 100 million years old.
Wow.
So a chance encounter, but it has given the Earth a moon which is very different from the others. And we know this from looking at where the craters are. They're not spread out equally, and we can learn the geological history of the moon from where the craters are. So we have a story which could even possibly be true.
Fantastic. And about how long is that story? How old is our solar system?
Our solar system is about 4.5 billion years old.
Wow, so 4.5 billion years old.
4,500 million years old, a long time.
That's
but
amazing.
It's still young compared with the universe, because we've measured the age of the universe also, which is 13.7 billion years. So we're newcomers, even so.
Great question. Thank you, Blake. We have another video question.
Okay.
Still down in North Carolina, this time from Jeremy. Let's take a look.
My name is Jeremy, and I'm a sophomore earth science student from Scotland Early College High School. And this is my question for Dr. Mathers. With the technologies we have today dealing with space, can we further understand and maybe one day send people to Mars?
Can we go to Mars?
Excellent
That's
question.
actually a really hard question. Let me just tell you a few things that make it difficult to go to Mars. One is it's a really long trip. It's much, much, much farther away than the Moon is. The Moon is about 250,000 miles away, and the closest that Mars gets is about 30 million miles.
Wow.
So it's already more than 100 times farther away, and it takes months and months to get there with the kinds of rockets that we can build today. Now, a couple of other things that are difficult about it. Astronauts do not actually do very well in zero gravity. Our bones dissolve. This is a problem. So some of you might know people that have osteoporosis when they're really old. That can happen to astronauts in a big hurry, that their bones can get weak. So we don't want that to happen. So we have to hurry, have to get there as quickly as possible. Another thing that happens to them is that there's something called cosmic rays, which are elementary particles, mostly protons and electrons, but especially protons, that come and pass through our bodies all the time. Now here on the Earth, we're protected from them by the atmosphere above us. In outer space, they're not protected. So it's another reason they have to hurry to get where they're going. So we have to get them to Mars in a very quick time. Then the other harder part is to get them home again. It's a lot easier to go one direction than to come back. So far we have not brought home even one grain of sand from Mars.
Oh my goodness.
So this tells you that it's a little difficult. Is there any new principle of nature that we have to discover? Probably not. I think we have ingenuity, and we have really capable team around the world, people thinking about this. But it's the way we would do it today with today's technology would be very big and very expensive.
Absolutely.
So we're not ready to commit to do something like that.
Great question. Thank you, Jeremy. Not only do we have our video questions, but we also have questions for our webcast viewers. I believe the results are coming in, so let's hand it over to Jordan. Take it away, Jordan.
Thank you, Aaron. Okay, we asked our webcast audience a little something about the James Webb Space Telescope that Dr. Mather is working on currently. We asked them which of the following 4 options are not a main scientific theme of the James Webb Space Telescope. And so when we look at the results that we have here, the first option they had was the assembly of galaxies. The assembly of galaxies is a main scientific theme of the James Webb Space Telescope. The second option was the birth stars and protoplanetary systems. This is also a main scientific theme of JWST. Our third option, planetary systems and the origins of life, is also a main science theme. And D, the formation of Jupiter's moon, is not a main scientific theme of the James Webb Space Telescope. Now, we had 40 of you out there in our webcast audience that chose D and were correct. We had 11, 6, and 5 choose one of the other options. So the majority of you got that correct. Good job. Back to you, Aaron.
Thank you so much, Jordan. And let's go back to those video questions. I'm eager to hear that next one. This one's coming from Carly in Alabama. Let's take a look.
Hi, I'm Carly from Albertville High School, and my question is, what are the pros and cons of infrared data versus visible light spectrum data?
Excellent question. So there are different types of light, and there's a type called infrared and a type called visible light. So what's the difference?
Okay. Well, the difference between different kinds of light is just the wavelength. They're all called electromagnetic waves, and they're all produced in similar ways. But the main difference is just the wavelength. So infrared light comes mostly from cooler objects than the sun. The sun glows very brightly, and of course our eyes are made so we can see what the sun is producing. If you need to sense infrared, then maybe you're a snake, because snakes can sense infrared and they can tell whether something is there by the heat radiation that's coming to them. Snakes see in the dark, and we can't. because they can detect the infrared. So it tells us very different science also. Because objects at room temperature can emit a lot of infrared radiation, but not shine on their own, we can learn about things that are like us, planets. We can see them glowing as they're young. The other one of the cool things about the infrared range, though, is that we can also see the most distant universe, because as the universe is expanding, the light that we're receiving from the most distant parts of the universe expands also. So when it starts out as visible light, but when we get it, it's infrared. So that's why we have, for instance, decided to make a telescope that's special for infrared radiation. So it tells us different science, and it lets us see farther. So that's why it's particularly interesting to us.
Very interesting. So the Hubble Space Telescope can see what type of light?
Hubble's telescope can see ultraviolet light, which is shorter waves than visible light, can see visible light, and a little bit of infrared.
And now the James Webb Space Telescope will be able to see what type of light?
We see a little bit of infrared, red wavelength we can see, and much longer waves, the kind that your body emits but you cannot see.
So we're going to be able to see a brand new picture of our universe
it's all new
once
picture.
James Webb is launched.
Yeah. We've had some infrared telescopes in space for a while, but they're all small, and they're just telling us that there's so much more to detect. So lots of science to discover.
Fascinating. It's so exciting. And actually, speaking of the James Webb Space Telescope, that is our next online question. So I believe we're having results come in. Go ahead, Jordan.
Thank you, Aaron. Okay, the results are in. We actually asked our webcast audience why the James Webb Space Telescope actually features a segmented mirror that folds. And the first option that our viewers had was that the width of the telescope couldn't fit inside the launch vehicle, and we had 12 people answer that. B was the folding design will increase the visible range of the telescope, and we actually had 10 of our webcast viewers that chose that. And for C, we had the folding design will increase the quality of images gathered. Only 8 chose that. And then finally D, the segmentation makes it possible to gather imagery in more directions. And we had 10 choose that. So we had a pretty varied answers here. Everything was pretty similar. And the correct choice, which 12 of you chose, was A. The width of the telescope actually can't fit inside that launch vehicle. Back to you, Aaron.
That's amazing. Now we are going to stay with the James Webb Space Telescope, and we have another video question, this time from Fidel in Georgia. Take it away.
Hi, I'm Fidel, and I'm from Union High School, and I was curious about how big the mirrors are on the James Webb Space Telescope, and how will its size affect the data we receive from it.
Well, okay, the James Webb Telescope has a gigantic hexagonal mirror, which is made out of 18 smaller hexagons. And the total size is about 21 feet across.
Wow. So
it's about 2.5 times as big as the Hubble telescope, which means it's much, much more powerful. It collects much more light and can give us a much sharper image at infrared wavelengths.
And we can see those mirrors right now.
We got them on the screen there, so you can see how small the telescope, the old telescope mirror is compared with the new one.
That is amazing.
And then it looks like they're showing us also an animation of the telescope itself.
That's right.
Yeah.
So how will this be able to fit inside of its rocket?
Well, it's a kind of, it's like the ship in a bottle problem. When you see somebody has made a ship inside a bottle, they fold it up and they put it in and then they pull on a thread so that it stands up. So we have to do something similar. We have to fold it up, and then after it's launched and outside the atmosphere of the Earth, then we take away the covers, then we turn on the motors and we pull on the cables, and it unfolds. A very large number of motors are required, but we figured this out, and it's actually a fairly standard kind of technology to unfold big things in space. We've never had to unfold this one before, so we're still learning how, but it's definitely a pretty standard process, unfolding big things in outer space.
And just seems so difficult, but just like you said, it's
well, it is
process.
difficult. I mean, it's one of the hardest things we have to figure out, because if it doesn't unfold, we have no science.
That's right.
And so we're doing lots of rehearsals, lots of practice, lots of little models, lots of medium-sized models, and finally the big model.
And where is this practice taking place? Here at Goddard Space Flight Center?
No, so far we're practicing mostly in California. The prime contractor for us, the lead organization, is called Northrop Grumman. So they have a huge facility near LA Airport. So we go out there to see the tests.
Excellent. We're going to go back out to an online question. We touched a little bit about this, the effectiveness between Hubble Space Telescope and James Webb. So take it away, Jordan.
Thank you, Aaron. Okay, so our next polling question was, we actually asked our audience out in the webcast, how will the James Webb Space Telescope be more effective than the Hubble Space Telescope? Choice A, which was not popular, we had 3 of our audience members choose it, was that James Webb Space Telescope will feature the ability to pick up very strong visible light signals. As we heard Dr. Mather mention before, that is not the main feature of JWST. Choice B was very popular. We had 23 of our audience members choose it, and that one was that James Webb Space Telescope will look deeper into space than Hubble. And that actually is the correct answer. Choices C and D, James Webb Space Telescope is smaller than Hubble. That's not true. It is bigger. And also, James Webb Space Telescope will operate much closer to Earth and relay data more effectively. That's not true. It'll be further out. And we had 3 and 4 choose those answers respectively. So you did very well with that one, webcast audience. Back to you, Aaron.
Thank you, webcast audience, and keep on participating in those polling questions. We have our next question, this time from Nicole in North Carolina. Let's take a look.
Hi, my name is Nicole. I am a sophomore student at Scotland Early College, and I have a question for Dr. Mather. As an astrophysicist, what is the biggest discovery made in research which you were directly involved?
Oh my goodness. Well, I think it's pretty clearly the Cosmic Background Explorer, or COBE satellite, that we built here at NASA Goddard. And so maybe I should tell you a little bit about that satellite. It was drawn on the back of a napkin in about 1974, and NASA here sponsored the development of it, so we got to launch it in 1989. And I'll tell you what it was for. We were trying to measure the primordial heat of the Big Bang, the radiation, the heat radiation that was there in the beginning of the universe. Now, I use the word beginning very loosely because we don't know much about that. But we do know the universe today is filled with this heat radiation, and it's pretty bright. It's just that our eyes are not able to detect it. So our job was to measure this primordial heat radiation to see if it's got the right color, which is to say spread it out like with a prism and see if it's the right brightness at every color. Also to make a map to see if it's equally bright in every direction. And so the predictions were from the Big Bang Theory that it should have what's called a black body spectrum, very precisely, because and we didn't have any other story that would produce that kind of explanation. And then the second thing is that the radiation ought to have hot and cold spots that are left over from the beginning. And we calculated they had to be there, otherwise we could not exist. Our story is that gravitation reaching across the universe can stop certain parts of the material from expanding and collapse back down again, make stars and galaxies and eventually planets and people. And so we're pretty sure those spots had to be there. So there were 2 big discoveries. One was the color is right to be the spectrum of the Big Bang radiation, and the other was the radiation is not uniform and it has blobs on it. So we made a beautiful map that shows the primordial pimples of the universe.
And that's what we can see right here.
We've got it on the screen. Yeah,
yes.
The pink and blue blobs. The pink ones are warmer and the blue ones are darker, cooler. And it turns out the cool ones are the ones that are going to grow up to become galaxies and clusters of galaxies.
Excellent. I believe you've spoken about this before. Back in 1989, you had an interview about this mission, and I believe that we have that interview on here.
Oh, yes, I think we do have it available. Are we going to play it?
No, we just took it out. I'm sorry.
Okay.
I was getting you all prepped and primed for it.
Well, I suggested we take it out because it proves that I've gotten older.
So rather than going to the interview, we are going to go back out to a video question.
Okay.
We're going to stay down in North Carolina, and this is going to be from Patrick for a question for you.
Okay.
Hi, I'm Patrick. I'm a sophomore earth science student at Scotland Early College High School, and I have a question for Dr. Mathers. Could better joint collaboration between international space agencies speed up the process of interplanetary colonization?
Well, my goodness, that's a good question. I should say that we already do cooperate a lot with international organizations in the space programs that we're doing now. The International Space Station is international.
That's right.
And we've had astronauts from many countries already go up to it and work there. The James Webb Space Telescope is an international project with both European and Canadian participation. We have participated with India. When India sent a probe to the moon, we had some instruments on it. So there's already a pretty active form of collaboration going on. Now, the way that we would do travel to the other planets like Mars is surely very expensive today. And so if we're going to undertake this, it might be that one nation doesn't have the resources to do it. But if the world said, well, this is important to us, we agree, we'll support it, then a lot of organizations around the world would be happy to help. There are tremendous reservoirs of talent in Russia, in Europe, in Canada, in Japan, and now growing in China and India.
That's right.
So many countries can do space projects, and I think collaboration is a good thing.
Very important, yes. We are going to go back out to our online polls. I believe we have more results coming in. Is that right, Jordan?
That is correct. Thank
All
you.
right.
Okay, so we know that Dr. Mather won his Nobel Prize for his work with the Cosmic Background Explorer. So we asked our online virtual audience basically what was the groundbreaking data that he collected that won him that prize. Our choice A, which only 2 people selected, was that evidence of the formation of Earth, and that was incorrect. Choice B, 3 people selected spectrographs of supernova 1979C, and that was not it. Choice C was the correct choice, and 23 of you chose that choice. Radiation patterns moments after the formation of the universe, and that was correct. That's what Cosmic Background Explorer did. And then choice D, only 4 of you chose infrared images of the collision of planets. So that was the correct answer, C. Excellent job. We had an overwhelming majority of you choose that. So right back to you, Erin.
Great job, participants. Let's go back out to a video question. This is from Kylie in North Carolina.
Hi, Dr. Mathers. My name is Kylie, and I'm a sophomore Earth Science student here at Scotland Early College High School. And my question for you is, do you agree with Stephen Hawking's theories?
Oh, that's actually an interesting question because he has more than one idea, you know. One of the things that was very surprising prediction that he made, well, let me back up a little bit. He's thought a lot about black holes. Black holes are places in the sky where the gravitational force is so strong that nothing can get away. In other words, it's like a star has collapsed in and become infinitesimal in size. So the gravitation around such a thing is incredibly intense, and not even light waves traveling at the speed of light can get out. So this was predicted a long time ago, like maybe 1930. I've forgotten the exact time when it was predicted. People laughed and thought we'd never find them. A few years ago, we started to see that they really exist. And there are a few ways you can find them. One is that when stuff is falling in, it gets compressed and very hot, and so we see the X-rays that come out from those black holes that are sucking stuff in. We still don't really know how they got started, though. We don't know whether the universe started off with black holes or if they were produced later by stars or galaxies. But it turns out there seems to be a black hole, a big one, in the middle of every galaxy, including
we can see an animation of a black hole right here.
We think there's a black hole in the middle of our own galaxy, even. So now, what does Stephen Hawking tell us about this? He's actually not thought so much about the astrophysics as he has about the mathematics of the black holes. And he said, and this is very surprising, he said black holes can evaporate.
Interesting.
And not very fast, extremely slowly. But he said they could. And this is a remarkable prediction. And we can't actually verify that by measurement. We haven't got any black holes up close, and we would have a hard time telling if they were evaporating.
We really don't want to get up close to a black hole.
We do not want to try that.
No, we do not.
Anyway, that's one of his more famous predictions.
Yes.
He's also written a little book called A Brief History of Time, and many people have seen it, in which he tries to tell us why time goes in one direction. And he might be right, but to tell you the truth, I wasn't convinced when I read his book. And so this is actually one of the great mysteries of science, is why does time go in the forward direction? And what does it even mean?
Very interesting.
We can't imagine it going any other direction.
That's
so
right.
I can't imagine a measurement you could make.
I think that's
but this is one of those wonderful questions.
Chat session.
So anyway, but Stephen Hawking says he's figured out why.
Excellent.
So we'll see if he's right.
Very good. Thank you for that great question, Kylie. We're going to go back out another online poll question. Here come the results.
Okay, we went back to the Cosmic Background Explorer and we asked all of our online participants, we asked them exactly, with COBE, which of the scientific instruments was Dr. Mather the principal investigator for? And actually only 3 of these are actual scientific instruments from COBE. Okay, so 4 people chose A, the differential microwave radiometers, and 7 people chose B, the diffuse infrared background experiment. And for C, we had 11 people, and that was the correct choice, and that was the far infrared absolute spectrophotometer. All right, and for D, we had 9 people choose cosmic origin spectrograph. The correct answer there was C, the far infrared absolute spectrophotometer. Back to you, Erin.
Very interesting. We're going to go back out to a video question down to Florida, where Richard has a question for Dr. Mather. Let's take a look.
Hi, my name is Richard, and I go to the Central Florida Aerospace Academy. I was wondering why we have waited so long to send the alpha magnetic spectrometer up on the space shuttle instead of simply sending it up with a rocket, and what current research it will be supporting.
Okay, so the question is about the alpha magnetic spectrometer. This was proposed a very long time ago, actually, and the aim of it was to tell whether antimatter is coming to us the way that we imagine it should. From deep outer space. We have cosmic rays, which are like individual protons or atomic nuclei that are coming to us. So we had a story that there should be some antimatter as well. And so this spectrometer was intended to measure that. And so it's been in preparation for a very long time. Then it was going to be launched on the space shuttle, and then we had pretty disastrous events with both the Challenger and the Columbia. And so after that, we said, well, maybe we won't send it after all, because it was dangerous to carry it and various things. So then the question was, the questioner asked, well, how come we didn't put it up on a regular old rocket? And 2 things. One is it really needs to plug into the space station to work. And the other one is it probably couldn't survive the launch on an ordinary rocket. And so the space shuttle solves both of those problems. So I guess that's the answer to the question. It couldn't go any other way.
And the AMS launched yesterday on board Endeavour.
Yep. And it's on its way to the space station, and it will plug in, and it will work for some years.
Excellent. So that concept between choosing the space shuttle, which will end later on this year, and between a rocket is really something that scientists need to consider when designing their missions.
Yeah. And well, the different shape and the different amount of vibration that you get for each different rocket really matters, because it's kind of scary how much they shake on during the launch. And you have to be a pretty healthy person to withstand it.
That's right. I've heard astronauts say that it's quite a ride, and you know that you're in space when you stop shaking. So it's for 8.5 minutes, you are shaking constantly, and then all of a sudden it just stops, and then you're in orbit. We have our final video question for you, Dr. Mather. This is from Josh down in Florida. Let's take a look.
Hi, my name is Josh. I'm from the Central Florida Aerospace Academy, and I was wondering, how does locating the cosmic background radiation as nearly a perfect black body, how exactly does that support the theory of the Big Bang?
Okay, so his question was basically, how do you know it? Well, the story of the Big Bang says it was extremely hot and dense in the earliest times, and that it had plenty of time to come to what mathematicians and physicists call an equilibrium condition. So that basically there's only one possible prediction coming out of the Big Bang about this spectrum. It should follow this particular formula that's called a blackbody formula. It's like the perfect radiator. And so we knew it had to do that, and there were lots of other stories about the early universe that said, well, maybe it wasn't a Big Bang. And so from every other alternative story, you can also calculate what is the spectrum going to be. So the answer was none of them could match this prediction. So when we went to measure the spectrum and it matched the formula, it meant all of the other theories had to die. And some people wouldn't give up anyway. But that was the main result, was that measurement. So do we have some pictures of how the experiment was done? Are we going to show that?
I'm sure that it is on right now.
Well, the picture that we're seeing there, that's the map of the hot and cold spots. There was a diagram of the FIRAS that I wanted to show also. And oh, there we go. That's the picture of the spacecraft, the Cosmic Background Explorer satellite. What we see there is big conical shield. Some of it's been cut away so you can see inside, and there's a tank inside that carries liquid helium. Where liquid helium can get the instruments down to 1.5 degrees above absolute zero, which is even colder than the cosmic microwave radiation. So that's what we had to do to make the measurement. But the rest of what you see is to protect the instruments and to provide electric power. So now they've got a diagram for you that shows how it was done, actually. Just to abbreviate slightly, the device that's shown is called an interferometer, which operates by splitting the incoming waves into two beams and delaying one and then coming back together again. So that's the technique of measuring the spectrum. The more important thing is we can take our Big Bang simulator with us. So there's a big chunk of black plastic in this picture, which is called a calibrator body, and it is supposed to emit exactly the same way that the early universe would radiate to us. So if we put this object in the antenna and we get the same answer we did when we were looking at the sky, then immediately we know the Big Bang theory is correct. And it was wonderfully simple.
And this is what you earned your Nobel Prize.
That's what the prize was for. Yep.
Fascinating.
Yeah.
Well, we've had some wonderful, we actually see you receiving your Nobel
Prize. Oh yeah,
Prize.
there I am with the king. And then a little while later I had the actual Nobel medal. The medal's about this big around, and it's very heavy because it's solid gold.
Oh my goodness, this I'm sure is bringing back memories for you.
Yes, it was quite a wonderful adventure to go to Stockholm to meet the king.
Yes.
And I got to meet his wife, the queen, and asked her about her children.
That's amazing. Oh my goodness. Well, we've had some wonderful video questions, and I'm sure we have some wonderful webcast questions coming in. And so we are going to go out to our webcast audience as well as our in-studio audience for their questions right now.
Good.
First, we have a webcast question from Ross. He would like to know your position on the Big Bang Theory. We've talked a little bit about this, but what is your position on that theory?
The position on the Big Bang Theory, we have measured as well as we can possibly measure enough to be sure the Big Bang Theory is as true as you can make it. We have no alternative explanation of what we see. So we're, despite the fact that this is a very surprising and almost bizarre theory that the universe is expanding from this incredible concentration in early times, we haven't got a better one. So this has got to be it. So my position is it's true.
All right, excellent question.
Of course, we're always expecting surprise in science.
That's right.
So we could be learning something about this Big Bang that says it wasn't really what it looked like. That would be exciting.
Very exciting. And while we're waiting for those webcast questions to come in, go ahead and then send those in. We're going to go out to our in-studio audience. Do we have any questions from our students today?
Yeah. Some people have been very patiently waiting for their turn to ask a question.
We have one in the back.
Way in the back, I see. Yeah.
Why are the mirrors?
Can you wait for the microphone, please?
Yeah.
Why are the mirrors on the satellites and the telescopes hexagons?
Why are the mirrors hexagons? Hexagons are pretty close to circular, so they're relatively easy to make. The other thing is hexagons will fit together in the pattern that you see, so you can make a complete mirror all made out of hexagons. So that's a basic reason. It's geometry reason why it's hexagons. And if we had more space, we could have had another ring of more hexagons around there to make an even bigger mirror.
I have seen these individual mirrors. They're just down the street here at Goddard Space Flight Center, a few of them, and they are huge.
Yeah, each one's about this big, and there will be 18 of them. But they're so lightweight, you'd be able to pick one up yourself. Well, maybe not the shortest of us, but you could pick one up.
Oh wow, that's fascinating. We have another webcast question, this time from Andrew at South River High School. He's asking, what is the redshift, and why is the expansion of the universe accelerating?
So the question is, what's the redshift? The redshift is the fact that we see distant objects and all of their wavelengths, the wavelengths that we see are all longer than they would have been if they were nearby. So this is called a redshift. The starlight looks redder than it would be from nearby. So that's the redshift, and we can actually calculate it. It's the fractional change of wavelength. And so it's basically is approximately the same as the fraction of speed of light at which something is going away. So if something's got a redshift of 0.1, it means it's moving at 1/10 of the speed of light. That's really fast.
Wow.
So on the other hand, we've got it figured out that sometimes they move so fast that the number is actually bigger than 1.
Wow.
So that means they're really far away. So this, we say, we have two ways of describing this. One is because it's moving away from us, and the other is that the space is actually expanding. And so we don't know what space is, but it could be expanding, whatever it is.
That's right. Very, very quickly.
So
Great
he had
question.
another question about something else on that.
Why is the expansion of the universe accelerating?
Why is the universe accelerating? We don't know, but we have a name for it anyway. We say there's dark energy, which is basically shorthand for we don't know.
Great question. Thank you so much. We also have another question on the webcast. This is time from Mark, also at South River High School. He's asking, what were time and space like prior to the Big Bang? And the second question, what in that environment do scientists believe caused the massive amount of energy required for the Big Bang to occur? Wow, those are great questions.
Those are hard questions. So basically what was there before the Big Bang is an unanswerable question. Because as far as we know, the Big Bang erased all evidence of the previous conditions. So we're stuck. We cannot actually see to the other side, even in our minds. On the other hand, we have mathematicians who are busy trying to make a good guess. So in the future years, we may be able to answer your question better. And there was another part of this question.
Yes. What in that environment do scientists believe caused the massive amount of energy required for the Big Bang to occur?
I don't think we have an answer to that question. But it could be that no energy was required. It could be that this is just something spontaneous.
Interesting. So maybe Mark one day will be able to be the scientist to answer that question himself.
Yeah. So we have things called quantum mechanical fluctuations in mind, and maybe it's one of those. Maybe our whole universe is a quantum mechanical fluctuation of some primordial material that came before.
Amazing. Amazing. Well, we're going to go back out to our audience and see if you have another question.
I think there were some questions people had, and don't get shy. We'd be happy to have them.
Don't be shy. Hi, I've been hearing a lot of discussion about just like how you're making theories based off of how the materials of the Earth are, and I was just wondering how much does that play a role in your overall assumptions of like how to you know, I guess I'm just wondering, like, could you explain a little more your theory and how it ties into some of your studies? I think I just want to get an overall understanding of that.
Okay.
Okay.
Well, to tell you the truth, I don't really have much in the way of theories, but a lot of other people do. So I'm pretty much in the business of let's collect some evidence and take some pictures and make some measurements. And then other people tend to figure out the theories that explain them. By the way, when people say a theory, in science we mean an all-encompassing story that fits all the evidence. So when Einstein gave us the theory of relativity, he said he made many predictions about what ought to happen, and we've never found an exception. So it's a very good mathematical theory. We've got formulas and ways of predicting everything. So we've also not found any exception to the theory of the Big Bang. We've seen the evidence that the universe is expanding. It was actually discovered in 1929, a long time ago, because Edwin Hubble saw that the distant galaxies are going away from us. So we've had this idea that the universe is expanding since then, and it had actually been suggested even before that. But Einstein made fun of those people and said they couldn't be. Nevertheless, he was wrong that time. So we have the story of the expanding universe. That's pretty sure. What's unsure is what was there in the earliest moments. Because we know if you try to take the laws of nature that we've heard about so far and discovered and tested, and you imagine what are they like when the conditions are so incredible, you can't imagine they really are right anymore. So we're got to guess. A lot of guessing going on about those first moments.
Absolutely. We have another audience question.
Okay.
My name is Kyle Stanley, and I'm from Reed Temple, and my question is, how do you see space exploration in the next 50 years?
Oh my golly, what is space exploration in the next 50 years? Well, I think that we're going to continue with the International Space Station for, what, at least 10 years more.
Yes.
Because we've got lots of experiments to do, and people are ready to go. For the near term, we don't have our own rocket anymore. We're going to be getting rides with the Russians on their rocket. So this is an example of the international collaboration that people talked about earlier. So we'll continue to learn from that about how to do space habitation. Right now, it's still an unsolved problem. How are you going to live forever in space? We don't have a farm. We don't have a way to purify all the water that we lose. So you cannot just live forever in outer space. You have to keep taking food and water.
That's right.
So this is not so good. You would think we would eventually have figured this out, but it's harder than it looks. Because making things do the right thing in zero gravity just doesn't come out so simple. So we've got a lot of engineering in front of us to be able to know how to live forever in space. When are we going to go visit the nearest other planet like Mars? That's really hard. And so I think it's going to take a long time. 20, 30, 50 years wouldn't surprise me a bit. So it's either difficult or impossible, somewhere between those two things. In the other end of things, we're going to have robotic explorers of all sorts. We've got robots already can drive around on Mars and on the Moon. It could even get to be where they're cheap enough to build that Disney will buy one and send it up so everybody can drive. I don't know. So it's really hard to anticipate the commercial part of space exploration. Entertainment turns out to be real popular. And there are people who are willing to pay their own money to go and get a ride into space.
That's right.
So if there are enough of those, then our world will change.
That's right. What may be science fiction today could be science fact later on down the road.
So if you had enough money, you could already buy a ticket. So this is pretty amazing to me.
Yes.
It's not just governments that are interested. So I think that if the public is interested enough, we'll be able to do a lot more than we can do today.
Fantastic questions. Unfortunately, we've run out of time today.
Oh, is it really?
Yes, unfortunately. I know. I've learned so much today. Thank you so much for joining us
thank
today.
You. It's a pleasure to be
Dr.
here.
Mather, it was terrific.
And thank you all for coming to listen and talk with us. Thanks.
Absolutely. Thank you for joining us both on the webcast and here in the studio. And finally, thank you to NASA Explorer Schools for hosting this chat. On behalf of everyone here at NASA Goddard Space Flight Center, good luck to everyone in school. Stay in school, find something you love to study, and maybe one day you'll be working here at NASA. Goodbye, everyone. Take care.